Can everyone see the slides, and do they actually change when I move them?
Yes, they do.
Okay, great. So thanks, Joseph. Hi, everyone. So I was asked to give a talk about kind of like a summary or overview of gravitational waveforms and inferences from them. So I'm hoping to give a kind of an overview of all the different binary neutron stars and neutron star black hole events that have currently been discovered and announced, as well as the gravitational wave models, the current plethora of different models that are out there for each of those systems as well. And so I'm just going to give a couple key features about each of the models and the references therein, so that if you find one particularly interesting, you can go and look at for more detail yourself. Just to get some credits out of the way, that all the events that I'll be talking about today, both for the BNS and the NSBH, were originally discovered and published by the LBK and have been referenced accordingly. And this material is based upon work supported by the NSF's LIGO laboratory, which is a major facility fully funded by the.
Jake, your slides are invisible.
My slides are invisible. Okay. What does that mean? Is it not moving, or?
No, we don't. You're not sharing your screen.
Okay. Is this working now?
We see your screen now.
Yes.
Okay, and the slides are changing?
That is correct.
Okay. I'm not sure what happened there. Sorry about that. So yeah, anyway, the events here were originally published by the LBK, and all the work here is supported by the National Science Foundation, and this particular talk isn't on behalf of the LBK. I also just like to emphasize in all these talks that the work done by the LBK is contributed from a bunch of brilliant people across a bunch of different institutions across the United States as well as around the world. So I always like to give credit to everyone involved. Okay, so here's a brief outline of the talk. I don't want to go too deep into the outline right now because I'll constantly be referencing it as we go through each bullet point. So let's just start out with the context. So as you may know, there are two major binary neutron star events that have been announced by the LBK. So there's 170817, and this was the first detection that also had the E&M counterpart along with it, as well as 190425. More recently, we have the two neutron star black hole events that have just announced. Was it like a week or two ago? And these are labeled GW200105 and GW200115. And while there exists, I'm sure as many of you work on and know, that there exist binary neutron stars and neutron star black hole numerical relativity waveforms, many of these can be too short or take way too long to produce and do not cover the full parameter range needed for direct use with our parameter estimation algorithms. And so what the LBK and others have done is use state-of-the-art models to estimate some of these parameters of the BNS and the NSBH events that we've seen. So these waveform developers are constantly trying to update and improve their models to, for example, to speed up their analyses. So if the waveform generation becomes more efficient, then that in turn speeds up the parameter estimation analysis. They also want to always include more physics. This includes higher order modes of the waveform, precession, as well as more tidal information, as well as being able to analyze more exotic parts of parameter space. Because as we'll see in a second, a lot of these models the validity region of these models are restricted to certain parts of parameter space. So expanding the validity range is always an important part of improving the models. Okay, let me just go over briefly some of the parameters that you're going to be seeing in this talk. So to completely describe the binary neutron stars and as well as the neutron star black hole systems, we normally use 17 for the BNS and 16 for the NSBH parameters. And that in turn is 10 intrinsic for binary neutron stars and 9 intrinsic for NSBHs, and then 7 extrinsic parameters. So for the intrinsic parameters, this uniquely defines the binary dynamic. So we normally like to use 2 mass parameters here. I've used Q, which is the mass ratio, as well as capital M, which is the total mass, the Cartesian components of the spin, so the primary and secondary spins. And this is the same parameters that is normally used for binary black holes, with the addition for the systems that involve matter with the lambda 1, lambda 2 parameters, which characterize or parameterize the tidal deformability. And for the NSBH, we normally set lambda 1 equal to 0, and we normally define the primary mass to be the black hole in an NSBH system. We also include some extrinsic, or there's also the extrinsic parameters, which represent the space-time coordinates and the Euler angles for the binary rotation relative to Earth. So basically where it is in the sky relative to us. And we also, in the bottom right here, I've also included some other parameters that we like to use for various reasons. So there's this chi-effective, it's kind of like a mass-weighted spin parameter that uses the z components of the spin, which is normally how we define aligned to the orbital angular momentum. And we're able to better constrain this compared to the individual spin parameters, as well as this lambda tilde term, which you can see is in terms of the mass parameters, as well as the lambda parameters. And this parameter can be weakly constrained and is how the leading order effect of the tidal deformation enters into the gravitational wave signal. Okay, so let's go over some of the binary neutron star events. So I'm sure, as most of you know, the first detection was 1708-17. And this was the first binary neutron star announced by the LVK, and it also included an electromagnetic counterpart that was measured in multiple different wavelengths. And so here I've plotted just or I haven't plotted, but I've taken figures from the O2 catalog paper published by the LVK, where we have the secondary mass versus the primary mass, the 2D distributions here for the 90% confidence intervals, with the 1D marginalized distributions for each of those masses on the top and the sides here, as well as the 1D marginalized distribution for lambda tilde. And each one of these colors represents one of these different binary neutron star waveform models that many of which we'll be talking about today. And one interesting thing to note about some of these comparisons between different model analyses is that they're noticeably, you do notice some differences between the waveform models, but they're still largely consistent, which gives us more confidence in our answer here. Another interesting thing to note about these results here is that all the models to varying degrees are consistent with lambda tilde equals 0. So the LVK also announced a little bit later about another binary neutron star that detected 1904-25. And this was actually the lightest system detected by the LVK, as you can see by the little table here of the different parameters. The difference here in the plot, so here I have the same M2 versus M1 plot. I also have Q, which again is the mass ratio versus this chi-effective. Remember, this is kind of this effective spin parameter that I mentioned earlier. And instead of plotting different waveforms here, what they plotted were the same waveform model, but with different spin priors. So the blue distribution is a analysis where the LVK allowed the spin magnitudes to go to higher spin magnitudes, and thus it shifted the posterior to higher mass ratios. It gained support for higher mass ratios. And this is a relatively quieter event compared to 1708-17. The SNR was lower. And in turn, this means that the posteriors are generally more broader, as you can see by these distributions compared to the previous figures. Okay, so now let's talk a little bit about the different models that are out there and the ones that were used in some of these analyses. So first we'll talk about the NR tidal models. So this type of model is a closed form approximate for binary neutron star coalescence with tidal effects that can be then attached to any binary black hole gravitational wave model. Now, depending on the base model, these can be non-precessing or precessing, but they've only been done for models that only include the dominant 2-2 mode of in the base model. And so the available models currently is the IMR Phenom D, which is the IMR Phenom family's non-precessing 2-2 only model, as well as an EOB model that's called SUB-NRV for ROM NR tidal. And again, these are both non-precessing models. And this also includes a precessing model that they've done where they've taken the base model of the IMR Phenom PV2 and attached this NR tidal to it. So how is this constructed? Well, they first extract the tidal contributions to the gravitational wave phase from some set of numerical relativity data. They then take the tidal contributions and they're employed to fix high order coefficients in the PN expression. And then in the frequency domain, the tidal approximates can then be built using the stationary phase approximation. And these were the models that were done in the figures that we saw on the previous slides. And one unique thing about these types of models, especially with the precessing one, is that this one is currently the main precessing model that is used in all of the LBK analyses. Okay, more recently, the same developers have developed a second version of these types of models. And again, some of the improvements to that they made in this V2 version is, so this closed form expression for the gravitational wave phase includes further analytical knowledge as well as improved numerical relativity data. It also includes a tidal correction to the gravitational wave amplitude, and it includes higher order spin squared and cubic and spin contributions to the phase. And here I just have plotted from the developers' work publication, just the waveform plotted with a comparison to a numerical relativity with the parameters with this in this table here. Okay, another type of model, tidal model that's out there is called SUB-NRV4T, and this is based off the binary black hole effective one body model that's been out for a while. That's called SUB-NRV4T, or sorry, without the T, just V4. Again, this is similar to the previous models. This is a non-precessing model. It only includes the 2-2 mode, and it's in the time domain. The validity region here, you can see, is that the two tidal parameters, lambda 1, lambda 2, only goes up to 5,000. The mass ratio Q is between, the 1/Q is between 1 and 3, and then the spin magnitudes can be between minus 0.5 and 0.5. Some interesting features about this model is that it includes dynamical tides, as well as later update to the model that includes spin-induced quadrupole moments at leading order 2PN order. And this is one of the models that was actually used in the O2 catalog published by the LBK, which again, this is the same plot that I had before of 1708-17. And you can see that this V4T model is here represented by the orange distributions in the 1D and 2D plot. Okay, so as I mentioned on the previous slide, that the V4T model is in the time domain, and it's a relatively slow model to generate the waveform. So what these developers have done with other collaborators is devised a frequency domain surrogate version of this model, SUB-NRV4T surrogate. And it has the same features as V4T, again, non-precessing, including only the 2-2 mode, the same validity region. It includes quadrupolar and octopolar adiabatic and dynamical tides. but the kind of the key feature of this model is that it's significantly faster, and depending on your initial frequency, between either 1,500 or 6,000 times faster than the time domain version of the model. And on this plot that I've taken from their paper, you can see V4T surrogate is in the green here, and we have a bunch of other different waveforms, some of which we've already gone over. So you can see that there's the two NR tidal models here, as well as the V4 ROM BBH model, as well as a PN model, Taylor F2. And you can see that the V4T surrogate, which is here is plotted in green, is comparable to all the other models that are currently being used. And you might be wondering how these waveforms generated by the surrogate compare to the underlying base time domain version of the model. And according to the waveform developers, the mismatches are no higher than 4.5 times 10 to the minus 4. So you kind of get these comparable accuracy for a significant increase with this surrogate version of the V4T model. Okay, another EOB model that's out there is called TOB ReSum S, and this is another but unique EOB formalism that includes tidal effects. This is, as well as with most of the other models that we've talked about, is a non-precessing model. But one unique feature about this model is actually includes higher order subdominant modes. So this particular model includes all the modes L less than or equal to 4, but it doesn't include the memory M equals 0 modes. And this model is also in the time domain. And we can see that it has a similar validity region as the previous models, but it actually goes up to 1 over Q between 1 and 6. And these incorporate slightly different tidal information. So this model particularly incorporates PN and self-force contributions to the tidal potential, as well as incorporating equation of state-dependent self-spin interactions. And again, this is one of the models that was used in the O2 catalog paper. Here, again, this is the same plot from before, just represented. The TOB ReSum S is represented with this pink distribution. Okay, and another more novel model is the hybrid NR surrogate tidal model. And this is based off the BBH hybrid NR surrogate with a similar name. And it has similar features to that underlying BBH hybrid surrogate. It includes all the modes. I forgot to mention that it is non-precessing as well as with the other models, but it includes higher order modes. So for this particular model, it includes L less than or equal to 4, as well as the 5-5 mode, but not including 4-1 or 4-0. The validity region of this model is slightly different. So you can see here that the 1 over Q is between 1 and 8, and the spins here actually go up to minus 0.7 to plus 0.7. And the base BBH hybrid NR surrogate is constructed via an interpolation of numerical relativity waveforms, depending on interpolating between the different numerical relativity waveforms that exist. And what they do for the tidal version of this model is the term they use is splice the post-Newtonian tidal terms onto the surrogate's binary black hole waveforms. And this combines the accuracy of the surrogate waveforms with the efficiency of PN. And I've taken one of the mismatches studies that they did, comparing one of the numerical relativity simulations. So here they've taken a binary neutron star numerical relativity simulation, and they've compared it to a lower resolution just to kind of have like a base comparison represented by this cyan color. They've compared the highest numerical relativity simulation to the base BBH hybrid surrogate, and that's represented by this black here. And then they've spliced two different PN models to the base hybrid surrogate to construct their different tidal models, as well as comparing the numerical relativity simulation to V4T, which we've already talked about. And kind of the takeaway here is that you can see that along with V4T, this spliced tidal hybrid NR surrogate for both of the different splicings perform significantly better than just the base BBH hybrid surrogate. Okay, so those were some of the, so we went over some of the binary neutron star events that have been announced. We've also looked at some of the waveforms used to analyze those events, as well as some more novel models. So now let's move on to the neutron star black hole events. So again, just a couple weeks ago, the LVK announced 2 new neutron star black hole events, GW20-0105 and GW20-0115. And again, here I have a similar plot as before, where we have just the secondary mass M2 versus M1. And you can see the 2 NSBH events are here represented by this orange-ish and blue distributions, with comparisons also to these 2 gray distributions, which are other events that have relatively high mass ratio, just for a comparison. And you can see from this table all the different properties of the different parameters of these 2 events. And some interesting things to note is that the primary and secondary masses are consistent with black holes and neutron star masses in population synthesis models for NSBHs. And the secondary masses are also consistent with the observed neutron star mass distributions in the Milky Way. So this gives the LVK confidence that these are relative confidence that these are in fact neutron star black hole events, although they are also consistent with binary black hole systems as well. And as you might be noticing if you're taking a look at this table, is that we actually have a parameter chi-p that tries to parameterize some sort of precession. And that's because for these particular results, we actually used the binary black hole models that include precession in higher order modes. And we'll talk about why that is on the next slide. And I just want to end this slide with the last note that there was no electromagnetic counterpart identified for either of these 2 events. Okay, to quantify the tidal effect of the secondary mass for both of these NSBH events, they used 2 relatively novel NSBH models and compared them to their BBH counterparts. So in these particular plots, we have this effective spin parameter chi-effective compared to the secondary mass for each of the 2 events. And for the different colors here represent different types of models. So you can see here, the 2 pink lines represents 2 different model families for NSBH. The orange here represents kind of the base binary black hole versions of those 2 models, as well as versions of those 2 models with higher order modes represented here with green. And as you can see here, the 2 pink curves and the 2 orange curves are relatively similar to each other, where we actually do see some differences when we include higher order modes. So the conclusions that the LVK drew from this is that there was no evidence of measurable tides or tidal disruption for either of the 2 signals, which is why the LVK decided to have their primary the primary analyses be of the binary black hole models with precession and higher order modes. Okay, so finally, let's just talk, because I know I'm running out of time a little bit, about the neutron star black hole models. So there were 2 used for these 2 events, the Phenom version, so IMR Phenom NSBH, as well as the EOB version, SUBNR V4 ROM NR tidal V2 NSBH. That one's kind of a mouthful. And just like their base model, these are non-precessing and only include the 2-2 mode. You can see the validity region is similar to the tidal ones, with the exception being obviously the Q, with the mass range being between 1 and 15. And both of these models use the same NR tidal V2 phasing applied to the underlying BBH model that we talked about earlier with the NR tidal models. And then as far as the amplitude is concerned, for the phenom model, the amplitude is based off of the BBH model IMR phenom C, which is an older version of phenom D, which we talked about earlier. And then the EOB version is based off of the V4 ROM and our tidal V2, and then corrections are applied for tidal disruption. And then let me just end, because I know I'm getting close to my time, is that a couple of the other models can also be used for NSPH, namely the V4T or the hybrid NR surrogate tidal model. But obviously the event would need to be in those validity ranges. So I think I'll just end it there since I'm running out of time. Thank you for your time.
Thank you. If you have any questions, please use the raise your hand option.
There is also the option like to clap people.
Yeah, thank you, speaker. Okay, we have a question. Masaru?
Yeah, I have very naive question. So these events were not originally announced as a black hole Newton star binary. So for example, 2150 event, so initially it was announced as a mass gap event, and so 2105 events it's a retroactive event. So what happened? So my question is that well, in the future, so similar thing could occur or what?
Sorry, I was having a hard time understanding the question, but
Yeah, for example, so 2015 event was originally announced as a mass gap event. So, but well, so maybe this is due to the very rough template or something like this, right? So,
I don't know if that's
maybe.
Yeah, I'm not sure if that's true, because I mean, I think the event was just announced a couple of days ago with the neutron star black hole coalescences paper, but I think whether it is a neutron star black hole event in particular will be better explained by better P as the waveforms are developed, more NSBH waveforms are developed to analyze these events. So I think whether the event is actually an NSBH merger or not, I think we'll become more and more confident as the models improve.
Okay, so that means that also in the future, so similar thing could occur. So.
There is one more question, I guess. So
I also see that there's some discussion happening in the chat. So Jacob, could you address the questions in the chat? It looks like the last two.
Okay. Yeah. So I think Salvo is helping to answer that question.
Okay.
About, I see what you, yeah. Okay. So Salvo clarified that I think the classification was for like low latency announcements for these events. So I think he's helping to answer that question. So someone asked, how are the deformability parameters lambda defined, and how are these related to tidal forces? So I can point you to a paper that kind of explains it better, but they're related to like, they're defined in relation to like the quadrupole Love number, as well as the radius of the neutron star, which is also related to kind of like the mass quadrupole moment, as well as the quadrupole electric type tidal field, which is, is basically the Riemann tensor components of the companion space-time evaluated at a star's center. And I can point you to a paper where I kind of you can learn some more insight into it, but that's what kind of the definitions are related to.
Okay. If there are no other questions, then let's thank the speakers.